Okay, this is part 2 of looking at some basic transformations for exponential functions, and continuing on, we're going to look at how all of these transformations are linked to the parameters capital A, B, C, and D. And firstly, even though A is not a parameter, it's the base, and we saw that with the base, if it's a decimal between 0 and 1, in other words, you get a decay function, and as we see it get bigger, it gets bigger than 1. Now it's a growth function. Let's just set it and then forget it. Let's set that on, say, something easy like a base of 2. So this is a base of 2, 2 to the power whatever is what we're dealing with. So let's look at these one by one. So let's look at a fairly easy one first, D. We can see at the moment that this has an asymptote which seems to want to approach the x-axis, which is y equals 0. Sorry, now it does. Sorry, there we go. That's because d equals 0. As we increase d, it lifts the whole curve up, so it's a vertical translation, as we've seen before, and the value of the asymptote is the same as the value of d. So if we put d up at, say, all the way up there at 10, the asymptote is 10, it's approaching 10, won't actually reach it. If we zoomed in on that, it's approaching that line y equals 10, but I could show you some zoom-ins if I had a bit more time, but it's approaching y equals 10. Y equals 10 is the asymptote. Okay, and note that d is 10, so that would be a plus 10 on the end there. So at this stage we would have y equals two to the x plus 10 if we just looked at those parameters only. So we can see that d is a vertical translation. If d goes below 0, the asymptote is y equals negative something, and it moves down. Okay, so increasing d translates the curve up, reducing it moves it down. So I'm going to put it back at 0 now, so we can look at just one thing at a time. The next one I want to look at is the other translation, x plus c. So when c is 0, you got your standard curve there. I might just go in a bit there. And if we make it c plus 1, have a look at which way it's going. Went to the left. Alright, c plus 2, 3. So as we increase that, it moves the curve, translates it to the left. We take it back to 0. It's in its natural position there. And then if we put it into the negatives, that'll be x plus negative 1, right there, which is x minus 1. So putting it there and just stopping it for a minute, we would have, let me get my pen, we would have y equals 2 to the x minus 1. Notice the x minus 1 is all as the index. So in general, the c translates it sideways. When c is positive, it moves it to the left, and when c is negative, i.e. x minus, we have it moved to the right. Okay, so it does not change the shape. But now for the two transformations that do change the shape, b. So we've got to look at b down here. So b does change the shape. It dilates it. Okay, so b, if b, like I said previously on the previous video, if we have a fractional index, it's the same as having a negative value for b. You can see that with negative 0.6. Okay, it's like those situations where we have a fractional index. It's a function that is a decay function. You can see it. But once b is bigger than 0, once it's positive, it dilates it. It vertically stretches it. So the larger B is, the more vertically, the more compressed it is horizontally, I should say. So that compresses it horizontally. Let me select the pen. Come on, pen. So that's a compression horizontally. It's a dilation. It's a type of dilation which changes the shape. Shape change. Behave yourself, pen. Alright. Okay, so here we go. We can see that if we decrease it, it's less compressed. Increase it, it's more compressed. I'm just sticking with positive values for B at this stage. So it's a shape change. So we'll just put that back at its standard position, which is 1. But if we put it back up to, say, 3, we see it's more compressed. In this case, then we would have the function y equals 2 to the x, and we would have a b of 3, so in fact that would be 2 to the 3x. Okay, so that compresses it horizontally. Okay, lastly we are looking at A, capital A on the front there, and we've got that A there, and basically it is a dilation too. It vertically stretches the graph. So while B was horizontal compression or stretch, A is vertical, so it's a shape change as well. So if we have a look here and zoom in a bit, maybe this way a bit, we can see its effect there. So as we increase it, it's a vertical stretch. Decrease it, it's less stretched. And then, interestingly enough, and this is something you'll probably look at more in the future, once it's negative, it's actually inverted. So this one here at -2 is the mirror image of when it's at +2. It's the x-axis as the mirror. Okay, so basically the important thing to know is a vertical stretch by a factor of whatever A is. So this one here, if we look at setting it at, say, 2.5, that would then be the graph of, that would be y equals 2.5 times 2 to the x. I'm just putting the brackets there so we don't have the 2.5 and the 2 run on together. Okay, so there's our 4 transformations I should say, and whoops, if we had to sketch the graph y equals -3 times 2x, sorry, having a bit of trouble with this thing, y equals -3 to the 2x plus 4, what would we do? Well, we have to look at each of the 1, 2, 3, arguably 4 transformations present, and then deal with them one at a time. So looking at what we got here, I would start with y equals 3 to the x. So if you look at the base function, it's got a base of 3 and it's just had some translations on it. So you know that the basic shape, and a sketch, remember, is just that. It's something that's a reasonable representation. It's not a precision diagram. All we're after is being able to see what you know about functions. That's why we get you to sketch them, because obviously a computer or a graphics calculator will do a better job. So it's just a sketch. So that's y equals 3 to the x there. Now we've got a few things going on. We've got, let's look at the shape. The shape has had a dilation. Okay, so it's got a compression horizontally. And we can see that the 2 does that. So one way of saying that it has a dilation from the y-axis of a factor of 1 on 2. So from the y-axis, it has a dilation of a factor of 1 on 2. Factor 1 on 2. Half. Okay, so it's compressed horizontally, okay, compared to what's going on the y-axis. It also has this one on the front here, which is a -1, and so what that does is inversion. So with so that was b equals 2, and here we've got a equals -1, and that doesn't stretch it vertically because the magnitude is 1, but because it's negative, it reflects or inverts. That's another word, invert, about the x-axis. Okay, and now we've got the other ones, which are the shape. Well, we've got no horizontal translation there. There's no x plus c, but we do have a +4. We have a plus d. So we could say c equals 0, d equals 4. So translated vertically, 4 units up. So it's going to be further up than it was. The other thing to note is that the asymptote therefore will be 4 units up. The asymptote, remember, is on the x-axis, or y equals 0. It'll be up, so it'll be at 4. So 1, 2, 3, 4. The asymptote will be up here. So ready to draw it now. So it's quite different to the original function. Let's have a look at that. And I might add too that I mentioned briefly an extra point when we were back up here. One significant point sometimes. This is one of those sometimes. So the point I've got in mind, well, went too far, is when you look at when x equals 0, what's going to happen here? So when x equals 0, we've got y equals -3 to the power 0 plus 4. So 3 to the 0 is 1. That'll be -1. -1 plus 4 is 3. So it's actually going to cut through there at y equals 3, and it's got the asymptote here, and it's going to be compressed, so it's going to actually do its thing a bit more quickly. So it's going to be a bit something like that. Okay, it's not going to be as gradual as that one is up. This one's going to fall down more steeply, and so we have a sketch of our function there. The last thing we want to do then is to use our graphics calculator to solve 2 to the power x equals 5. This is how we would use it using software or graphics calculator. So if we've got 2 to the power x equals 5, so let me select that one. I've already got that saved. So actually I had 2 to the power x here, there, and what we need to do is have that in the line y equals 5 as well. So I've already got that there, and it's basically where the intersection is, and we have 2.322, so that means that when x is 2.322, we have y equals to 5. So the solution is x equals 2.322. So in finishing, putting all this together, we've got the following points there for A, B, C, and D. A is the dilation factor, a shape changer, by a factor of a vertically. That is, the graph is stretched vertically when a is bigger than 1, and it's compressed when a is a decimal between 0 and 1. If a is negative, it is reflected. So if a is less than 0, that's reflected or inverted in the x-axis, like we saw just then. The constant b dilates the graph by a factor of the reciprocal of b from the y-axis. In other words, it's compressed horizontally. Probably more handy to know the second part of that. It's compressed horizontally when b is greater than 1, and when b is a decimal, it's stretched horizontally. And constant c is that translation there, and basically it's to the left when it's plus, and when it's x minus, i.e. c is less than 0, it's to the right. And d moves d units up or down, including the asymptote, depending on whether d is positive or negative. So it moves every point, including the asymptote, which is related